I don't remember, one of the people had asked me. So now let's descend down back into the world of ordinary convexity and make a few connections right now. So I'll start with the simplest kind of convexity, which is a simplification of this. So you might say that actually this came later in time. So maybe Carl Menger, when he created this, he looked at Jensen's definition. So somewhere around 1905, Jensen wrote the most influential paper in convexity, where he defined convex functions. And I put this paper up on the class webpage. It's in French, but it's still readable. Because most of it's in math, so you can read it. So, but in this paper, towards the end of the paper, Jensen, he had great foresight, and towards the end of that paper, he says that someday it should be, or it might be recognized that these functions are as important as positive or continuous functions in real analysis, and their power will come to be witnessed. So in 1905, he said that, and of course now everybody does convexity all the time. So, but it's a very nice paper. Many of the things beyond even what I'm going to describe, Jensen already describes in his 1905 paper. So it's worth looking at it at least. And for those of you, like I said, doesn't really matter what language it's in. If you get the chance or the time to read some of these older papers written by the masters, I encourage you to do that. Because say what I'll present in class or what you'll see in a textbook is a compressed, refined version of stuff that has been around for a long time. But if you want to be more creative, invent your own things, it really pays off to look what was that guy thinking when he came up with this idea. So it's always worthwhile, if you of course have the time, to go back to the master's paper and learn how they developed the whole subject. But anyhow, so after that story, so Jensen originally started looking at this. So let's right now come back to simple R, where the absolute value x minus y is our distance function. So on that space, so we'll say so now we are leaving the domain of convex sets, keep them at the back of your mind, and now we'll start talking about convex functions, because we want to now play with some objects on these sets. So on that set, Jensen looked at these types of functions and much more generalized versions of these. So we say that f is convex if it is if it satisfies this midpoint convexity property. This essentially is coming from suggested from that. So another way to read this property, you've seen it maybe hundreds of times. One nice way to read it is f of the arithmetic average is smaller than the arithmetic average of the f's. The notion of averaging points is very intrinsic to the notion of convexity. If you figure out different ways to average x and y, you can use those different ways to create other notions of convexity. Because convexity, thought abstractly, right, is just trying to capture or talk about stuff that remains inside a set. What is the mean doing? An average is also looking at stuff that remains between the extreme points. So that's why these two concepts are extremely intimately related to each other. And means are also very intimately related to metric spaces. Because once you can average, you can also compute distances. But okay, let's not worry too much about that. So this is called midpoint convexity. Even until the 70s, people in real analysis who really are masochistic, they were looking at all sorts of different properties that can be concluded about these functions. And I'll just call them mid-convex or midpoint convex. And for us, general convex function on R, we'll call it convex if it satisfies, it's a matter of taste to write it as a closed interval or open interval. So this is what is called a convex function. And of course, a convex function is midpoint convex, but as you realize, not vice versa, right? A midpoint convex function, as we saw with example over rationals, need not be convex. So this theorem is attributed to Jensen, though Jensen looked at, here this is averaging, he looked at rational combinations and then you can pass to limits. But before I prove this, I'd like to prove this theorem that, however, when f is continuous and midpoint convex, then it must be convex. The reason I like to prove this theorem here is I very frequently end up using the comfort of verifying midpoint convexity while proving convexity of certain functions. So as soon as they are continuous, then you can do that happily. So it's good to once go through that proof. And by the same record now, once we have written that as the definition of convexity, with a slight operator overloading notation, in our, suppose we were in this fancier metric space, then we say that f of the rest remains the same. So what I've done here with operator overloading here is, by that notation, I mean really nothing but, that's just what I previously denoted as gamma of alpha. So with that plus sign, I just mean, travel a distance alpha along the curve. So, but with that overloaded notation, now x's and y's, so this is the point on that curve, x's and y's come from a general metric space. And if they satisfy this Jensen style inequality, we'll just call f is a convex function on that metric space. So that's what I'm not going to go deeper into these types of functions right now, but just to tell you that really most of it is operator overloading with some technicality. So we'll come back to this technicality later when we actually look at these types of functions in greater detail. So let me go through, I wrote down a short little proof which I think is worth putting here. We'll attribute it to Jensen because that's what is done by textbooks. So let's just say it was Jensen 1905. If f is continuous, so let's okay, if f is a continuous midpoint convex function, then it must be convex, which means a continuous, so okay, I'll just call it MC, midpoint convex function. This is actually an if and only if, right? Because if it is convex, then clearly with alpha equal to half, it's midpoint convex. So the non-trivial part is the following direction. So you can come up with several proofs, I guess, but maybe a little picture, the standard picture we see of convex functions. If it's a convex function over some interval, so suppose it's convex within this interval, outside this interval whatever it does we don't care. So this is whatever the lower half of the interval, upper bound. So on this interval f is always below that line formed by the values at the end points of the interval. And to try to show this proof, a kind of strategy could be to assume that it is continuous and midpoint convex but fails to satisfy this full thing. So if it doesn't satisfy the full inequality, then certainly there must be some small interval in there somewhere where it has a little bump in the wrong direction, and then try to from that arrive at a contradiction. So I'm going to write down here which I think is the shortest, at least the cleanest proof of this. It's not my proof, because my proof with contradiction looked somewhat ugly. So let's call this inequality, we'll just call it star. That's our convexity inequality. So suppose it is midpoint convex, but that inequality breaks down somewhere. Suppose that's what we have assumed. Then look at this function. So if you look at this function, and if that inequality fails somewhere, then clearly there is some alpha in this 0, 1, actually strictly inside 0, 1, where this function g of alpha is going to be strictly positive, right? So the its maximum value that g of alpha can take somewhere in that interval is going to be strictly positive, because this thing is violated. Well, then out of all those possible, so that means, you know, if this is violated, implies maximum value of g on will be, say, some number m strictly bigger than 0, and stuff is continuous, so it's this cannot become plus infinity. So now out of all the possible places wherever it gets that value m, it can have several points maybe where it gets that m, pick the smallest. So let alpha 0 be the smallest value of alpha in 0, 1, where g of alpha 0 is m. So I'll leave this here, and what happens then? So essentially we'll try to now construct in that small interval, select distinguish points which break the midpoint convexity rule. That's all we have to do to get a contradiction. I'll just give you one selection here for lack of time. You can come up with other selections. So, you know, let delta be small enough such that alpha 0 minus delta and alpha 0 plus delta still are in the valid 0 to 1 range, and we can pick that. Then comes the, again, coming up with these really clean choices of alpha, etc. It's not hard, but it still takes a little bit of time. This is one of those rare cases where I am happy with the proof by contradiction. I'm not always happy. These guys will continue lying inside the interval. After this is up to you. You gotta see what happens to f of, because f is midpoint convex, this holds, And by plugging in these x and y's, x bars and y bars, you want to now write everything in terms of G, which you can. That's the definition. So the homework part here is to show this. It's like one line of algebra, but slightly messy, so I'm not writing it here. G of alpha 0 will be every hypothesis, every statement made here. So alpha 0 was the smallest value of alpha for which m happened. So that means, and m is the maximum. So for alpha 0 minus delta, that particular guy will be strictly smaller than m. This guy might be less than equal to m, but the whole thing is going to be then strictly smaller than m. But g of alpha 0 was equal to m, so you have your contradiction. So this is, I think, one of the prettiest proofs I've seen. There's another proof in Boyd's book which uses continuity by using binary number induction. You can also do that if you want. I really like this super simple proof. So this shows that as soon as we have continuity, midpoint convexity suffices for us. And that makes me happy because there are functions. So I'll show you exactly now as an interesting example. I think I'll already show that example to you, why I'm a fan of midpoint convexity. Before we construct all sorts of detailed convex functions, yeah.
Why can't m be positive infinity?
Because G is continuous, so it has to be bounded.
But the integral is not compact.
Oh, we are strictly inside. So if you're saying that 0, 1 is not compact? Or what interval is not compact?
Can't it just keep going on down?
Oh, we are only looking for alphas in this 0, 1 range.
But like 1 over x.
1 over x, you have the infinite domain. So continuous functions on compact domain
Have to be bounded. But
We also know that G of 0 and G of 1 is 0.
Okay.
good point. Well, another important thing to note there is, if the maximum were achieved at either 0 or 1, were achieved at the endpoints, then by definition the rest of the function is underneath that line and we are happy. But so let me show you an example of this midpoint convexity. How about this function? F of x, unfortunately I'm starting with functions on matrices, but say log determinant of x. So if f is convex, so if f is convex, then minus of f is called concave. And so now on the set of strictly positive definite matrices, so you can call, if you want, you can call them Hermitian positive definite, or let's just look at real symmetric positive definite matrices. This set P of, let's put it n by n real symmetric positive definite matrices or Hermitian matrices, doesn't matter. That function, of course, there are several different proofs that it is concave, because minus log det of x is convex. So this is the concave function. I'm just going to show you a proof to introduce some matrix notation in there. So let's verify the following. So in case there is anybody who's not fully comfortable with matrix algebra, there is, at best I'll point you to some references, or we can talk offline. I will cover some matrix analysis related stuff later in the class when Alex is also back. We'll cover several matrix related things. So already right now, if you don't feel super comfortable with matrix analysis and algebra, please spend some time outside the class to gain more facility with that, because later once we start discussing matrix concentration theory, etc., you'll need to know that stuff. Anyhow, just a short entertaining proof of that. So proving that that thing is concave is equivalent to proving that determinant of, so I'll just verify midpoint concavity. Actually strictly concave, but let's just write that. So we'll prove this thing. All the matrices are strictly positive, definite, invertible. So one proof, there are several proofs possible from here. One proof that I like here is, now divide both sides by determinant of x. What do you get? Identity plus x inverse y by 2 is bigger than determinant of x inverse y. Okay, now what is the determinant? Determinant is just product of eigenvalues, right? So this thing left hand side, so let lambda I x inverse y be the eigenvalues of that product. So the left hand side is just product of 1 plus lambda I x inverse y by 2, whereas the right hand side, this is what we want to prove, is just product, sorry, there's a half gone from there, square root of lambda I, and so this is nothing but, 1 plus lambda I by 2 is bigger than square root of lambda. That's just the arithmetic mean geometric mean inequality multiplied n times over, and that gives you a quick proof of course it's not an elementary proof, it uses one little trick. This arithmetic geometric mean inequality wants its argument lambda to be positive. How do we know that lambda I is positive? You have to claim that somehow, right? So x and y are positive definite matrices. The eigenvalues of the product are going to be positive. And the proof for that is as follows. So let's leave this here and you can set this guy up. So lambda I, so just write lambda of x times y is the same as lambda of let's just say x to the minus half times xy into x to the half, because you know that eigenvalues remain preserved under similarity transformation, right? So if you have a matrix A and you do SAS inverse, eigenvalues of both guys will be the same. It's just change of basis, that's all. Change of basis doesn't change the eigenvalues. Well, this thing is lambda of x half y x half. X half y x half is a positive definite matrix, because you know if y is positive, then any z transpose y z for arbitrary z remains positive. In our case, x is symmetric, so x transpose and x is the same story. So with that you have shown that the eigenvalues are positive. But be warned that the product xy is not positive definite matrix, okay? Only the eigenvalues are positive. So, okay, so this was a proof that I like about that. It's just to show that there are many other proofs of these functions, either you could prove these things using calculus, so, or you can prove them directly using arithmetic mean, geometric mean inequality. A lot of functions we can just prove convex by this direct brute force without resorting to calculus. So for the brave amongst you, means if you feel tempted to use calculus, so now let's just make a list of some of the ways that which I assume that you already know. Okay, have a read Boyd and Vandenberg's chapter 3, different ways of verifying convexity. Continuous functions, midpoint convexity, or if it's differentiable. So I'm not going to write down all the ways here, I'll just assume that you know. If it's twice differentiable and Hessian is semi-definite everywhere, then the function is convex, right? All these like several different ways. So what I'll do in the lecture notes is put together a nice list of all the ways that we know on how to detect convexity. Yeah.
How do you know that log beta is continuous?
Oh, determinant is a continuous function. Determinant is a multilinear polynomial in the entries of a matrix, so it's a continuous function. And from there, so composition of continuous functions, etc. So yeah, you have to know all these things, but determinant, like permanent. So determinant, one way of writing the determinant is the following, which should be a quick, so det of x for any matrix is just a sum over all permutations of I is 1 to n, ai minus 1 to the sigma, that's the signature of the sign of the times sigma of I. So it's just an alternating multilinear form in the entries of the matrix, and hence it's continuous. Okay, so but what I'm saying is we have lots of ways of detecting convexity. Okay, midpoint convexity is one of them. Sometimes doing differential calculus is easier, sometimes it's not. And for those of you who might be addicted to checking second derivatives to verify convexity, here is some medicine. So this is the challenge question for today. There was an open problem mentioned last time, but this time this is semi-open. So challenge question. So let x1, x2, xn all be strictly positive. Let's define functions. h1 of x is 1 by x. Everybody can prove that is convex either by calculus or without calculus. H of 2, let's say x1, x2, this function is also convex, not so easy to prove it, but can be done with differential calculus for those people who know how to use Mathematica. But H3, pretty soon Mathematica will also die if you try these things on it. So 1 over x1 plus 1 over x2 plus 1 over x3 minus all these pairs plus 1 over x1 plus x2 plus x3. And you can continue for hn with these alternating sums. These functions are convex. They arose in some application actually in probability theory where somebody was analyzing some coupon collection, etc. So they have some, but it took very clever simplification for somebody to then turn the problem into this, and then they said, oh my god, how to prove convexity of this guy. Because when they were doing some kind of log likelihood maximization, etc., God knows what not. So that is a challenge problem. If you figure out a good way to prove that those functions are convex, it will be quite impressive. Because they are actually even more than convex, but the proof is not so easy, and people who love taking second derivatives should try taking those here and convince themselves that maybe that's not the best way. Anyhow, so But sometimes second derivatives are awesome, right? Minus log of x. Everybody knows how to differentiate it. So for the rest of the class now, I will actually follow Rockefeller's convention. So far we had been looking at convex functions, f, say from Rn to R, but it makes our notation slightly simpler if instead of looking at functions that go into R, we adjoin to it essentially plus and minus infinity, though mostly plus infinity. I don't care about functions that get the value minus infinity, because when we are optimizing, we are trying to minimize f, and f happens to be minus infinity. That's not so great. But so just some ordinary convention that will, but you know, once you start dealing with infinities, it will make the subsequent notation nicer, but you have to set up some conventions on how to deal with infinities. So for example, you might introduce simple rules like x plus infinity is infinity plus x for all minus infinity is less than x is less than equal to plus infinity. Like several such whatever natural rules would come up if you were to think of infinity as the largest number. It's not a number. So you make such rules. One of the important ones in there is the following, that we will write 0 times infinity is the same as infinity times 0 is 0 for all, and minus of minus infinity is plus infinity. These are standard conventions, you can say, but these conventions don't conflict with the standard ordering convention that we have on the field of real numbers, so it's okay. We can continue using these conventions. And important convention, the infimum of an empty set is defined as plus infinity. That means if you're trying to optimize over a set that is empty, you say plus infinity because you couldn't optimize. That's a very nice convention. And so similarly, if you're trying to maximize over an empty set, we just say supremum is minus infinity. And as usual, like you don't particularly enjoy dividing by 0, try not to do infinity minus infinity. So that's one thing you have to watch out for. We create these conventions, but you know, expressions of the type infinity minus infinity will remain invalid. People in physics are allowed to do that. We are not.
Why is 0 times infinity?
It's just a convention.
But then infinity minus infinity, like, you can extend.
So we allow multiplication with scalar, but we are extending the definition of what scalar multiplication means, but we are not extending what addition or subtraction fully means. So again, like I said, these are conventions and they work really well for us. So typically, for what we'll do now is we'll always have f defined on entire Rn to this extended set of real numbers, and by domain of f we mean the set on which f is smaller than plus infinity. So whenever, you'll also see that in other textbooks or Boyd's book, whenever we write dom of f, that is just the set on which f is smaller than infinity. That means it takes a real value. And usually we request that it have a non-empty domain. Otherwise, if it's plus infinity everywhere, good luck minimizing it, right? So that's a reasonable convention, but it's an important convention because it allows us to write the following, right? F of x, 1 by x, and plus infinity otherwise. So 1 by x is now, by this definition, this f of x is convex on the entire real line. Or it just simplifies, it will simplify notation as we start doing optimization. So you can just, if it simplifies for you to think, you just think that, you know, f has some domain of definition where it's non-infinite, and wherever it's not defined, set it to plus infinity, can't hurt you. So that's roughly our convention. Okay, so I want to already, I think we are, today I am trying to cover half the stuff of last time, so I think we'll be in good shape. So those of you who have not already done so, I recommend to you that you read chapter 3 from Boyd and Vandenberg. It's very easy to read chapter, but definitely read that. And let me just mention a few very important convex functions, because of course we cannot list all of them, but some of the ones that we will maybe meet now and then in the class, let me mention those here. And if we have time beyond this challenge problem, I'll mention to you another. This one is in n variables. I'll mention, if we get time, a problem of testing or proving that a function is convex, which is just a function of a single variable. I don't know how to do it right now, but maybe somebody in the class can figure out. So let's see, this one can be used again now. Where did I keep the? That's where the chalk was hiding. There's so much chalk hiding back there. So this convention of infinities, let's put it to use already and look at some very nice convex functions. My favorite is the following. So let C be some subset of R to the n, let's say non-empty subset. So almost always whenever I write let C be a subset of R to the n, please prefix to it the words let it be a non-empty subset. So then we define a function delta of C as follows. So delta is defined on entire R of n. It's 0 if x belongs to C, and it's plus infinity if x does not belong to C. So this thing is called an indicator function. It just indicates whether you're inside the set or you're not inside the set. And it's a small exercise for you to verify that this is a closed convex function if and only if C is a closed convex set. So when I say closed convex function, I mean the following. Associated to any convex function f, we can write its epigraph. So in less fancy words, if this is f, the set, the space above the graph is the epigraph, is just this set x comma t belonging to, let's say, Rn cross R, such that f of x is less than equal to t. So often if in your reading of any papers or books, if you find the word closed convex function, all it means is that its epigraph is a closed set. That's what it means. So delta of C is one of the most important convex functions for us. It looks kind of boring, right? But it comes in very handy when we do optimization, just for simplifying notation. And we'll see, maybe, already in the next lecture, when I start talking about optimization problems and how to solve them, we'll put this to good use. Next favorite function of mine is, okay, not so favorite, but let's just write it. So let's C again be in R to the n. Support function of C is sigma C of x is just supremum over or let me write it with a z here and an x here. And so more generally, so this is convex, and the reason it is convex follows from, you can say, the more general claim that you might have seen already, but let's write it here anyways. This is a very easy to verify claim, but by far one of the most important ways to construct convex functions is the following little statement here. So h of x comma y is a family of functions indexed by y belonging to some arbitrary set. So now if h of x comma y, if h of x comma y is convex in y for each x, just pick some x, for if for that x h of x comma y is convex, then f of x obtained by doing supremum over the entire family is convex. You can verify that easily because supremum will be subadditive, and this one will imply that support function is convex. This is really very important. One alternative way of thinking about this is, I don't know how much this intuition will help you at this stage, but maybe at some point. So in the world of convexity, so in probability theory, you do summation to marginalize out or do integration to marginalize out variables, right? In the world of convexity, the role of that summation or integration is taken by supremum. So marginalization out, the act of marginalizing out in the world of convex functions is taken over by sup. So, and this connection is important because, well, it's just important to know because there's an entire field in algebra called max plus algebra and tropical algebra where people actually exploit this connection. Anyhow, that was a side remark. Another very nice consequence of this is from a paper by Werner Fenchel. You can say father of modern convexity. I put this paper on the class webpage. Definitely have a look at it. In 1949 he wrote that paper, and those days I think those people used to be quite economical with words. In 5 pages he describes maybe more than we'll be able to cover in the class because there are so many things in there. So he created the idea of Fenchel conjugates formally there, and I'll tell you more recent research about the world of Fenchel conjugates next time when we talk about them. But let's just define those here. Unfortunately, this is not so readable in this color. So again, so let f from Rn to R bar, the extended real numbers, be any function, okay? Not requiring f to be convex, it can be any function. Then define the following function. It's called f star of z . I like to write z in the first argument instead of, means of course, you know, these are just vectors, x transpose z, z transpose x, but that convention has a reason for writing it in the first place. Z is a linear operator acting on x to give you a number. So I usually like to write z first. Just keep, anyhow, so this thing, what did I write? Yeah. So this thing is called Fenchel conjugate, and it is convex, follows from a previous theorem. But what I want to tell you about the world of Fenchel conjugates, before I show you why we are interested in Fenchel conjugates, I need to tell you one more related thing. Or maybe it's I should show you an example of a Fenchel conjugate. Okay, let me just show you some more convex functions of worthy of our attention. before we put these definitions into action. It seems that I might have made some bug here. Okay. So the next class of convex functions that we really care about are norms. You have already seen norms so far, right? And I'll just write this for you here. So the norms that we care about on vectors are the so-called LP norms. So let's say 1 is less than equal to p is less than infinity. This norm is defined as and if p is infinity, then it's written as the max norm, which is given by max of. So these are vector norms. Another vector norm worthy of knowing about, this one shows up in machine learning papers now and then, is the so-called LPQ mixed norm. So suppose x is along some kind of vector which I've so suppose x is a big vector, you chop it into subvectors, exactly, partition it into subvectors. Then so suppose we split it into these subvectors. So x is basically just stack x1, just putting that arrow to highlight it's a subvector. Then this thing is a commonly used norm, though with very specific choices of p and q. You take the p norm of the q norms of the subvectors. And what is a simple theorem that we wish to prove? The theorem that you should try to prove is all norms are convex. These are just LP vector norms, but more generally, a norm is any function f which Rn to R which has the following properties. F of x is non-negative and equal to 0 if and only if x is equal to 0. So that's the positive definiteness property. Then f of lambda times x is equal to absolute value of lambda times f of x. This is called positive homogeneity. And of course the most important property is that f of x plus y is less than equal to f of x plus f of y. So any function f that fulfills those axiomatic things is called a norm, and instead of writing it with an f, we usually write this double bar symbol for it. Okay? So you can prove using those axiomatic definitions of what it means to be a norm, you can prove that every norm is convex. Now, but going beyond vectors, let me also quickly tell you about norms on matrices. So most people will be familiar here with some norms on matrices. So there are several ways of defining norms on matrices. One way is, you can say, the engineering style, which is, I guess, the most commonly used style because it's so easy, is to just think of a matrix as a box full of numbers and treat that big box as just a long vector and just apply any of these LP vector norms to that. That immediately gives you a norm over matrices. Another way is to think of a matrix as a linear transformation that turns vectors in one space into vectors in another space. Then it's more common, though it's not used so much in machine learning, to use what is called an operator norm. So suppose this is any norm on vectors in Rn, and without loss of generality, I'll just right now write everything using n by n square matrices, real matrices. Whatever I'm saying very naturally extends to rectangular complex matrices without any change, but let's just write it with real numbers here. Then for a matrix A, its operator norm, so I'll put a subscript V here to highlight it's a vector norm. The operator norm induced by that norm is defined as apply A to the vector X, take the vector norm, see what is the largest possible, essentially largest possible scaling that your matrix can do of the vector. So this is called an operator norm. And again, just to test whether you are doing fine in linear algebra, we'll you can say sort of homework is to prove that if we are using the Euclidean operator norm, then that is nothing but sigma 1 of A, where sigma 1 of A is the largest singular value. Again, the operator norm of any complex m by n matrix A is its largest singular value. It requires to be proved, and it's a proof that you should be able to do to test whether you'll be fine with the subsequent matrix theory that comes up. But it's still, I should warn you again, sometimes, hopefully nobody in here, but has happened to everybody at some point in their lives, that people think that the largest eigenvalue is a norm. The largest eigenvalue is not a norm, largest singular value is a norm. But only for a positive definite matrix, only on the set of positive definite matrices will the largest eigenvalue be a norm. Otherwise, for general matrices, it's the largest singular value which gives you the norm. So you have to be a little careful about that, but that's about it. There are two more distinguished, of course, now that given any norm on space of vectors, you can construct a huge family of these matrix norms. There are two distinguished ones, which is called the slight, okay, I'll just write it one here, though later I'll abuse notation and this will mean something else. This is called the operator 1 norm, which is the induced norm that comes by using L1 norm, sum of absolute values on the vector space, and the infinity version, which comes by using the max norm, or the infinity norm as people call it, over the vector space. And it's an exercise in linear algebra to prove that the operator 1 norm is just the max sum, absolute value sum of columns. So the column with the largest sum in absolute value gives the 1 norm, operator 1 norm, and then by symmetry, the infinity norm is the largest absolute row sum. These are used, they are sometimes interesting in graph theory, but most of the time we don't see these because they are not somewhat unwieldy. Maybe the most common norm, which I forgot to mention here, is say A is, I'll just write it in full glory, m by n complex matrix, then it's so-called Frobenius norm in honor of Frobenius, who was a master of matrix theory. It's just given as trace of A star A square root, and why people love it is because you can write it like this in terms of just the entries. And of course, if Aij had real entries, this would be just Aij square. I wouldn't need that absolute value sign in there. And this norm is because it's very tractable. Once you square it, then it becomes very nice to work with. So these are kind of, so the operator norm and the Frobenius norm. The other class of norm which you might encounter if we talk about matrix completion problems or something at some point are, okay, let's actually leave those there, and maybe I'll just write those norms up here. So suppose you have a matrix A, sigma of A lists its singular values, and again this is an implicit convention, but I'll just say it only once explicitly. Whenever I write singular value map of matrices, it means the singular values are given in sorted order decreasing, okay? Fortunately, MATLAB also implements this convention. SVD command in MATLAB always gives you sorted diminishing. MATLAB somehow it doesn't implement this for eigenvalues because eigenvalues can be complex, that's why it doesn't. Singular values are just non-negative real numbers, so they can be sorted. So sigma of A gives you singular values. So there is a norm called the Schatten P norm, which is just the vector P norm of the singular values. And it's actually a very famous result of John von Neumann that which characterizes which norms can be written as norms of singular values. So there's an if and only if, but we are not going to prove that. And within the class of Schatten P norms, the most popularly used one is what people call the trace norm, or the nuclear norm. They write it with a star here, some people write it with a TR here. It just means the sum of all the singular values. So the trace norm or the nuclear norm or whatever it is called, for me it's just the Schatten N norm here, is just the sum of all the singular values. So these are essentially the matrix norms, and again the reason we'll just limit to these is it's an interesting question actually. I told you what the induced 1 norm is and what the induced infinity norm is and what the induced 2 norm is. For other values of P, for most other values if I remember correctly, computing this is NP hard. This was formally, it was kind of believed but formally shown maybe 5 years ago, maybe 4 years ago only. So of course those are theoretically interesting results which sometimes come up also in theoretical computer science. But okay, those were all the norms. There are more, but I'm not going to speak more about them. The final norm I want to tell you this one can be deleted. So to every norm you can associate its friend called its dual norm, its counterpart. And so if this is any norm on Rn, we define, this is a definition, dual norm let's say U star is defined as the largest value of U transpose X such that so that's a compact set, the supremum is actually attained. So this is an asterisk, sorry, bad handwriting. That's called dual norm. And the dual norm, by its definition, proves quite handy. So how many of you are familiar with the Rogers-Holders inequality? You might have seen it many times in life, right? So essentially, this is Hölder's inequality. So X transpose Y is less than equal to the norm of X times the dual norm of y. And Hölder's inequality, it essentially, all it says is, if the norm is an LP norm, and it's an exercise maybe on your homework, or maybe this is too easily found in textbooks, that the dual to an LP norm is the so-called LQ norm, and that gives you Hölder's inequality. This is much more general. So this holds for all norms. So dual norms, people kind of study them because they allow you to give these tightest possible inequalities. They come in quite handy there. And we'll see later, once we start doing optimization, how to actually exploit this fact. And what I might ask you, okay, one final thing. I don't have time to prove that, so I will leave you with the following exercise, which is, I think, very important, because it's also particularly nice because this one exercise captures several of these functions that at least I like. Let's see by the end of the class how many people actually like these functions. So if this is any norm, let's just write x in there right now. What is its Fenchel conjugate? F star of z, which is the Fenchel conjugate of the norm is not the dual norm, okay? Fenchel conjugate is defined as following: supremum over whatever so I had initially written down the proof to show you, but maybe what you can try instead is to show that, because I don't have time to prove it, to show that f star of z is nothing but the indicator function for the dual norm ball. So if f, what do I mean? So if f of x is the primal norm, you try to compute its Fenchel conjugate. The Fenchel conjugate of a norm is a convex function, and that convex function is an indicator function, and it's the indicator function of dual norm ball that I had wanted to show you, but the time ran out. So if I leave that up there, you can try to show that by just exercising this definition. And maybe the hint I'll give you is exactly divide the analysis into two cases. One is when z star is bigger than 1, and the other is when z star is less than or equal to 1. And at some point you might also want to use this inequality. So that kind of zooms us through Fenchel conjugates, norms, dual norms, matrix norms, etc., etc. And next time onwards, we'll actually start doing optimization, because now we have a common language to speak with. I didn't talk any bit all about other forms of convexity beyond this geodesic convexity, like log convexity, log concavity, but those topics we will touch as the need arises. So everybody is recommended, if you haven't already done so, to read chapter 3 of Boyd, and to at least try your hand at a couple of the exercises that I just mentioned in class like that. Okay, see you next time. Oh, one question. Of course, I know the answer to this is no, but Alex wanted me to ask you how many people are really stoked about coming in on Monday? So the answer is what I told him, but he wanted me to ask this nevertheless. So see you guys on Wednesday. Hi.
So I'm registered for the class right now, but I'm someone PhD student, right? And my professor is saying that he doesn't want me to register for too many classes, so I may have to end up dropping and not even